Yeah, we are live on YouTube, and we're good to start. All right, cool. So I would get started with the basics of electronics, the essential topics related to electronics. Yesterday we covered quite a good amount of basics in terms of understanding what robot is, what are the applications of robots, and how you would be able to build your own robot. I mean, that's the essence of it. Today morning we had a session on mechanics of robotics, and session now would be electronics. The session post this is programming, and that will give you a good understanding of the robot fundamentals. Right. To get started with electronics, I would probably get to understanding what electronics is all about. So if any of you could tell me what electronics is, what you know about electronics, because this is not something that we study in depth in the school. To a great extent, it's something that we study in applied sciences and not just in pure sciences. So anybody, what is electronics?
We can say it is a science which deals with the study of electronic components or the components which are made up of semiconductors.
Okay, right. So it's to do with electronic components, circuits, and all similar kind of things. So the word electronics is derived from the word electron, and basically it refers to the electron. And I say this to most students and teachers that if you can understand how electrons behave in various situations or scenarios, you will be able to understand electronics. Like you can probably consider it like a cakewalk. All you have to understand is how these electrons behave in an atom or a material or in a circuit. So, like the Wikipedia definition says, it's a study of how to control the flow of electrons, and deals with circuits made up of components that control the flow of electricity. So everything to do with electronics is electrons flowing from one point to another, either in a circuit or in a component or in a system. Now, this is primarily part of physics. So you learn more of electronics in physics. And applied physics is where you learn in terms of electronics and electrical engineering. Now, the difference between electrical engineering and electronics engineering is just that electrical deals with high voltages, voltages that are beyond, say, 5 or 10 volts, and a little higher. And electronics is primarily to deal with a lesser voltage and more to do with circuit components. All right. Now, what you see on the right side here is the atom structure. So what you see in the center is the nucleus, which consists of a proton and the neutron. And what you see around it is the electron. Now, there is a lot of hypothesis in terms of what is the structure of atom, how it looks. And over years, we've seen a lot of scientists proposing different models of how the atom looks like and what are the components of atom. And I believe this is also evolving in terms of our understanding how the system is. So there is no one way of very certainly telling that this is exactly how the system looks like. But with every experiment, people come up with their own models and going. And this is what we understand, that the center of the atom is the nucleus, which consists of neutrons and protons, and then there is electrons which revolve around the nucleus in orbits called orbits. And every atom of an element has a particular number of electrons, neutrons, and protons. It is standard to every atom. So out of all the 118 elements or elements that we know of, every single atom of these elements are unique. And this uniqueness is only about how many neutrons, how many protons, and how many electrons are there in that particular atom. That's it. So if you are able to increase the number of neutrons and protons and electrons in a particular atom, what is oxygen could become nitrogen, or what is carbon could become something else. But it requires a huge amount of energy for you to do those changes, and that's primarily the reason why there are chemical reactions and all of that, and all the whole of evolution chemistry happens. Now, for us to understand the components of the atom, the next slide basically talks of what it is. And what you see as pictures here is actually part of our course material that we give across to students and teachers, which more often we teach it in form of cartoons or animations where they know, okay, this is an easy way to relate to. Like we said, protons and neutrons combine together to form the nucleus of the atom. So they're always in a way where they're together. So that, since proton and neutron is a very heavy when compared to electrons. When compared to electrons, protons and neutrons are very heavy. So they constitute to be the core of an atom. And what's around them is electron. So protons are positively charged, electrons are negatively charged, and neutrons, they don't have any charge. Now, you can consider them like a solar system where planets are revolving around the sun, just that the planets don't run from their orbit to another place, but the electrons do. Some electrons jump from one atom to another, primarily not the electrons in the center of the system, but those electrons that are around in, say, you would call the outermost orbit. Those electrons are a little free to move around, and that's why they jump from one atom to another. But you have to consider that this is what is causing all of these things with electronics and current and voltage and all of that. The ability of those electrons on the outermost orbits or shells of an atom to move from one place to another. Yeah. So electrons revolve around the nucleus along the orbit, and those electrons which are on the outermost shell, when they move from one atom to another, is where they make a difference in terms of electric current and voltage and all of that. So I hope this is very clear to you, and I mean, you've studied this in school, you teach this to students in school. So this is something that needs to be like very clearly understood. Our understanding now would only be about what electrons do now. Where do electrons, what happens to electron? How do you make electron move from one place to another? What causes electrons to move? And this is what we will learn in electronics. Okay, now when you zoom in an atom and all of that, just to get a perspective of what is available or how small is electron, you will have to probably zoom in so much that it's almost, I don't have a count for this number, it's like 100 million times zoomed in. And by special electrons and all that. So these are very, very tiny. So a good comparison to that would be this. A human body is made up of approximately 7 billion atoms. And that's 7 followed by about 27 zeros. It is just to say that if you look at the size of atom or the electron or how things are, it's so small that it's absolutely invisible. Even with the strongest of the microscope, we will not be able to see it. And how do people ascertain that, okay, this is how it might look like, is primarily because of the properties these entities exert on the, suppose I'll apply some voltage on a particular component, and the way it behaves will tell me certain features about the electron. And then I do something else, and then there is certain behavior of the electron, and then that tells me a different feature. With all of these things put together is where we are able to figure out, okay, this is what electrons are doing, and this is what is a property of electrons, right? So for example, electrons were one of the first things to be actually discovered before proton and neutron. Electrons were discovered first, and then they discovered proton and neutron. Primarily because when electrons were on the orbit, they realized that there is something at the center which is primarily holding on to the electrons around, and then they realized that it is the proton, which is the reason why an atom is of neutral charge. But then they realized that protons itself is not causing the weight of the atom. The weight of the atom is because of something else other than proton, and then they discovered neutron. So this has happened over years, over hundreds of years, where we have come to a stage where we are today in terms of telling this is exactly how an atom looks like. And that's what we need to be appreciative of. So let me take an example of copper. Copper is a good conductor of electricity. We all know that. Copper is very commonly used in terms of electric circuits and everywhere. Copper is present everywhere around us. Now, why is the reason that we use copper? In terms of, so yesterday when Vibha was covering a session on cost versus benefit, telling with respect to the cost and the benefit that if you have to put it together, copper is the most optimum material to be used in electric circuits, or to be used in wires and all of that. You could use gold because gold has absolutely very, very low resistance when compared to copper. But I do not use gold because gold is very expensive. The cost that I will have to pay for gold wires is so much high that I would rather not have them. So I would use copper. But there are still places where I use gold. For example, processors, RAM chips, your computer RAM, your motherboards. There are places where there is a good amount of gold deposited, primarily because they need very high conductance at that particular place, and they do not want to compromise. You are using copper. So, and because gold reacts very less with the atmospheric air and all the moisture that's present, and that's the reason they use gold, because the contact surfaces, if it actually has some oxides on it, they become non-conductive, and you don't want after some time that your computer suddenly starts working and you don't know why it stopped working. Right? That's the reason why gold is used, primarily to improve conductivity. And the second thing is to ensure that there is no reaction with the environment and the components work and stay the way it is for a very long time. So in copper, if you look at what happens as atom, as a material, there are a lot of free electrons in copper, which means, like I told you, the outermost electrons on a copper is primarily about 2 electrons are free, which means they have the ability, they're very far from the center of the nucleus that they are usually running around here and there. When I say running around here and there, you should always remember, no electron from this end will come to this end very quickly. This is something that you need to keep in mind. They don't just randomly jump from here to here. They probably will, from here, they will come to the next one, and this probably will come to the next one. And that's how they go. You will not have one electron just running from one end to the other end without causing the other electrons to do nothing. So that's not something that's going to happen. We assume that these electrons move in something called as a dominoes effect, but even that is again debatable, whether electrons hit another electron, this electron hits another electron, and then goes. This is something that is debatable, but we do understand that these free electrons is what causes copper to be a conductor and not an insulator. Now, another feature of electron is that the like charges repel. I mean, this is a very common phenomenon that we have seen, and this is like a universal law. We say like charges repel, wherein electrons repel each other. Let's assume a situation where in this particular room that I'm sitting, I put a lot of electrons in the room, like maybe about 1,000 electrons in the room. I just let them in through one of the doors, all the electrons. Imagine the electrons are like water droplets or air particles. They just come into the room. Can anybody tell me how these electrons will be arranged in this particular room? In what fashion, what order? Will it be a straight line? Will it be a zigzag line? How will the electrons be arranged in this particular room?
Zigzag?
Zigzag, okay.
Randomly, as gas room is filled of gases.
They will try to occupy the space of the room as much as they can.
Right. They'll try to occupy the space of the room as much as they can.
Anywhere, everywhere.
Anywhere and everywhere, right. So it is like the electrons will start occupying the room in such a way that they try pushing the other electron away from them, telling nobody come near me, nobody come near me. And when that happens, you will find that the electrons are equally placed from each other, at equidistant from each other, and the electrons are spread across the room. So if there are 1,000 electrons and I say this is the room, the electrons from one electron to another electron, there'll be equal space. And the moment I remove one electron from this room, provided I have the ability to remove one electron, I remove one electron from this room, what happens is the remaining electrons again rearrange themselves to spread out equally. So this is the ability of electron. You should always understand electrons repel each other. but they will not be able to walk out of this room because they don't have a pathway to go out of the room. The moment I create a pathway, so which means I'm trying to tell you that, let me just use, I would request the participants actually turn off their video because it'll disturb the others during the program. Okay, so when we look at the electron as such, when I say I have a room where I want so this is a room, and I'm just drawing here. This is the first time I'm trying to draw using a and this is another place. Now I said I have a lot of electrons here, right? And I said that equidistant placed. Now I have another room where there are no electrons, right? And what happens when I try to connect a conductor between this and that? So for that, I'll have to just maybe use this and then say I have a conductor from here to here.
Brijesh sir, you have unmuted yourself.
So your mic is on mute.
Okay, sorry. Thank you. So I had basically dropped out because of a power outage. The internet went down and came back. I'm just sharing my screen again. This is the screen. Share. Okay, all the boxes I drew is gone. I'm going to draw it again. So we were talking about having two boxes that basically are something like this. I said there's one here and there is one here, and I have a lot of electrons here, right? So if I have an electron, so this is one electron and this is one electron, 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 another electron, another electron, another electron. What happens to the electrons when I try to bring a conductor from this point to here? I connect a conductor from this point to this point. What happens to all these electrons? These electrons will now start moving from this point to another, such that the number of electrons here and the number of electrons here is going to be the same. So half the electrons there were going to come here, and This is gonna go there, this is gonna go there, this is gonna go there, this is gonna go there. And this is how it's gonna be. There are equal number of electrons on both the sides. Now, this is typically what is actually what you call the function of current and voltage. When I said there were a lot of electrons in the first place here, it meant that this is at a higher potential when compared to the other point, because here there were no electrons at all. So can I say this is at zero potential and this is at a higher potential? Yes, but you need to keep in mind that this is a higher potential of electrons. It is a higher potential of electrons and not a positive voltage. So it's a negative higher potential. Do not get confused. I'm just trying to tell you in terms of electrons that there are a lot of electrons at one end and there are no electrons on the other end, which means this is at a higher potential when compared to the other system. So the moment I connect a conductor from this point to this point, all the electrons here will start flowing to here till the number of electrons here and the number of electrons here are equal, which means they flow till the potential becomes equal. Okay, and all of this we are talking about is only electrons. We are not talking of anything else, right? Okay, now that we have electrons moving from one point to another point, can we consider this as electric current? Yes, I can consider this as electric current, and primarily it is the flow of electrons.
Right.
Is that clear?
Right.
Yeah. So we are talking about electron current, like how you have water flowing, you'll say water current. You have air flowing, you'll say air current. Similarly, here we will call it electron current. Okay, great. Now this we understood. Electrons moving from a higher potential to a lower potential is where electron current forms. The more the electrons here, which means the higher the potential at this point, the greater the force in which the electrons will flow down to this point. Yeah, the lesser the number of electrons, the lesser the force with which the electrons will come down to the other point. Okay, and we are talking only about electrons. We are not talking about anything that's to do with positive charges. Great. The next slide for us is talking about current and voltage and how these things happen. Now you see a lot of electrons here, which is called the source of electrons, the higher negative charge density, and we call this the drain, which is the lower negative charge density. So I have a lot of electrons here, no electrons here. The moment I connect a conductor between this and this, I have all the electrons from here moving to this point, provided the number of electrons here and the number of electrons here are same, then it will stop. Okay, cool. Now what happens when you look at this? You have a lot of free electrons moving in one direction as they experience the force of repulsion from the other end of the wire, which has more electrons. Okay. Now we are talking about these spots where there were electrons before, but now there are no more electrons. Okay, there are points around in the atom where there was electron a little while ago, but there is no more electron because that electron moved to the neighboring point or around the neighboring atom, which means it created a void. It created a void in that space, and we call that a positive charge.
Okay, hole, you can say.
Yeah, you can call it a hole, but yeah, it's a little advanced electronics, but yeah, you can call it a hole. We basically say that there is no electron. It basically is referring to the feature that spot was supposed to have electron, but it doesn't have electron. I don't call this as a space where it's positively charged, primarily because if this was supposed to have an electron and I have removed this electron, only then this spot is called a positive charge or a hole. Okay, so similarly, in this particular system, there are a lot of holes that gets created. And in which direction is the holes moving? They're all moving in the opposite direction to that of electron flow. Now, electron current is coming in one direction, but the holes are moving in the opposite direction. There were a lot of electrons here, but now all the electrons have come here, which means all the this has become a positively charged system and this has become a negatively charged system. So your electron current is in one direction, but your positive current, which we actually call the electric current, is in the other direction. That's the reason why they say let's consider that the current is flowing from the positive to negative and not the negative to positive. So this was supposed to be what you see here as drain is supposed to be the positive charge. This is supposed to be the positive charge because there are less number of electrons when compared to this. And electrons started flowing in this direction. But what effectively happened is holes started flowing in this direction, and this is what we call electric current. There are two things, electron current and electric current. And for us, we consider the electric current in all the circuits and drawings that we do, primarily because we give importance to the positive charge when compared to the negative charge. Is that clear? Why do we consider electrons moving? We say current is flowing from the positive of the battery to the negative of the battery. It is primarily the electric current which is flowing, which means electrons are flowing from here to here.
Right.
Okay, great, awesome. So this is one understanding that you need to keep in mind with electronics. The moment you get this, it's very clear. It's very easy. All I'll have to know is now what is voltage? Voltage is the difference in the energy that is here and the energy that is here. That is voltage, nothing else. What is current? The current is rate at which the electrons are moving from one point to another point. That is current. Okay, great. So this is voltage and current. I'm not going to the textual definitions because that is not important to us. What is important to us is when I connect a battery to a circuit, I don't cause fireworks and Diwali on my circuit, so that I understand what exactly is happening, which connector to connect where, and what is happening to each of the components when I'm making connections. That is what is more important than the definitions for us. So I'm just going to clear all my drawings and move to the next slide. We're going to do a little bit of hands-on now after this, trying to understand what happens. A lot of you would have seen this picture in a lot of places. This primarily a very good depiction of Ohm's law, or we call how a resistance functions and how current functions and how what voltage is and all of that. Now I'll just read this out for you a while. It says voltage is what makes the electric charges move. Okay, because of the potential difference. It is the push that causes the charges to move in a wire or other electrical conductor. This is the voltage, the potential difference. This is what pushed the electrons from here to here. So it is a phenomenon. It's a feature that's of that particular system where it's causing the electrons to move from one end to another end. So you can consider this as a force that is pushing the charges, but it's not an actual force. There is no, somebody is not applying this force. There is no external force, but it is something that is causing electrons to move from one point to another. So this is what causes the current to flow. And because of this, we say voltage causes current, and voltage is proportional to current, or current is proportional to voltage. Depending on the number of electrons here and here, the difference between this point and this point, you will have the electrons moving from that point to another point, the speed at which it moves, or the amount of electrons that pass through a particular point in the conductor changes with respect to the electron density difference. Suppose there were 100 electrons here and 100 electrons here. What would be the current? The current will be 0 because the potential difference or the voltage is 0. There is no force that is acting on these electrons. So this is what is important. Okay, great.
It means, so there is no flow of electrons if both the sides are having equal number of electron.
Exactly. There is no flow of electron, which means suppose this is a battery that I have. I take a wire from the positive of the battery and connect it back to the positive of the battery. Is some current flowing through the wire? Nothing is flowing because the potential here is the same. The one end of the wire is at same potential when compared to the other end. So what is the potential difference? The potential difference is 0.
True, sir.
Yeah. Got it. So this is with respect to potential difference, voltage and current. And what is resistance? Resistance is something that causes the electrons to like slow down. It is not completely blocking. If it blocks, it's called a insulator. It is not blocking the resistance. It is like putting a speed hump. You've seen speed bumps on the road. What does it do? It will slow down the vehicles that are moving, which means effectively it slows down the number of vehicles crossing a particular point at any given point of time. So it slows down the number, I mean, the number of vehicles crossing this point reduces because of the speed hump. Maybe 100 bikes are moving on a road. You put a speed hump, effectively, and what used to happen is, if without a speed hump, 100 bikes used to pass every 1 minute. Now, because of the speed hump, here only 50 bikes are passing. Here there are 100 bikes coming. But what happens, because of the speed hump, eventually all of the circuit here gets slowed down. Now, the entire system becomes in such a way that only 50 bikes are passing through this point any given point of time, or in one minute. So effectively in the entire circuit, because of one resistor in one of the path, the flow of electrons slows down. And because this slowing down happens, we say that the current has reduced. Though the voltage is the same, there is enough force available to push the electrons from one point to another. But what happens is the resistance is causing electrons to slow down. And because of this, the effective current in the circuit is slowing down. And which means, what will there is so much of energy available, right? So that the electrons are running like, I'll go kind of a thing. So there is some amount of heat that is generated on the resistor. Because electrons want to go, they want to rush in and then just go through the resistor. There is some amount of heat that is generated on the resistor. And if I want to utilize this heat energy, I can use it. You see applications in heaters, water heaters, and all of that. What happens is effectively the same thing. I pass current through a particular wire, which heats up because it is slowing down the flow of electrons. That's it.
Excuse me, sir.
Yes, ma'am.
The slide on the screen is current and voltage, and I suppose you are telling something else.
No, I'm talking of current and voltage. Same thing.
Okay, sir. Okay,
it's the same thing. Yeah. And what happens effectively when you're talking about voltage and current and passing through a resistor, if this resistor is of a very low value and you have a lot of electrons flowing, then the resistor heats up. And because it heats up, it will glow. And this is what is a principle of an electric bulb. What Sir Thomas Alva Edison invented or commercialized as a bulb is the same principle. If you flow electrons through a tungsten wire, the tungsten wire will glow, and this is what gets to you as an electric bulb. And this is the same phenomenon. I'm trying to use the concept of voltage and current and trying to get multiple functions done. It could be heating, it could be lighting, it could be sound, it could be what else? Mechanical energy like motors. All of this happens only because there is a potential difference. I'm allowing the electrons to flow from one point to another. Instead of just flowing through a wire, I put another component like a bulb or a buzzer or a speaker or a fan or a motor, and then these electrons do some work so that in action you see either light or heat or rotation or motion on one of these things. So this is what is the principle of voltage, current, and what you call as load. And I said resistance in the earlier terms. We are eventually moving it to load. And this is what causes all that you see around with respect to electronics and circuits and all of that. Now, we just speak a little bit of resistance. Like we know voltage is proportional to current, current is proportional to voltage. But if you want to replace a proportionality, then you will have to bring in something called a constant, and that constant is resistance. And this is how resistors look. I'm sure you have seen resistances here and there. And
yes,
since
sir, I just wanted to ask, suppose for example, if you're taking a geyser, water geyser, so you said that if there is speed of the electron movement is slow from one point to another point, because we are adding some resistors in that. So you mean to say if there are more number of resistance, then the energy produced is more? Is it like this?
Yeah, okay. It's a very good question to look at it in terms of what is available, but let's also look at the voltage that you're applying. Say, for example, I'll just take this example so that you understand. And we all know this formula, right? I is equal to V into V by R. V is proportional to I. I mean, we know that. And then I replace it with a constant called resistance. Now, if you look at what I have to do, let me just tell you. There's the drawing. Okay. So I say that there is a heater. Okay. So please excuse me for my drawing. I'm very bad at doing this drawing using a mouse. So this is a heating coil. What is this heating coil? This heating coil is nothing but a stretch of wire that I've wound like a spring, just because I want the length of the wire to be more, but I can't have my tank to be this big. I want the tank to be small. So what I do, I wind the wire in such a way that I don't have to use a lengthy wire. So this, what I do is what I keep it on a conducting plate. Now, when I give a voltage to this point, so what is the voltage that I'll give? I'll give a 230 volts AC, right? 230 volts. And what is the voltage here? 0. Primarily because this is a live wire and neutral wire. And because there is so much voltage available, and this is nothing but a conductor, but which heats up because you're allowing more current to flow. This will heat up. Now, you're telling if I increase the amount of resistance, what will happen? Actually, if I increase the amount of resistance, the heat will come down, because what I give here is same, right? And I've only mentioned the voltage. I have not mentioned the current. Your water heaters are never connected to 1 amp sockets. They're always connected to a 16 amps socket. Are you aware of it? And your water heaters are not just 100 watt like your electric fan or TV. Your water heaters or geysers are at least 1 kilowatt or 1.5 kilowatt. That's about 1500 watt. 1000 watt to 1500 watt. When that's almost 10 to 15 times that of your regular fan on the ceiling. So if I increase the resistance here, it will try drawing more current. And if your circuit is capable of giving that much current, then it will heat up. But if my circuit is not capable of giving current, then I will not be able to heat the water. It's a very simple principle of I is equal to V into, V is equal to I into R, where I say, as in when I'm increasing the resistance, if my voltage is the same, but my current keeps increasing, instead of drawing 10 amps of current, it will draw 20 amps of current. And if your circuit is not capable of giving 20 amps of current, there will be a short circuit.
Okay, sir.
Okay. Yeah. So what happens, you cannot just connect the geyser to any plug socket in your house, because the socket in your house is 6 amp socket. Maximum current it can give is 6 amps. If you connect your geyser to that socket, a small socket, using a small converters that you get, what happens is your MCB, the main circuit breaker at your home, will trip, telling that you have drawn more current than expected, right? Because if you look at a 1.5 kilowatt system, are you able to see my calculator? 1500 by 230. Are you able to see my calculator?
No, sir.
No, sir.
No. Okay. Okay. Yeah, I just did 1500 divided by 230. It's come to about 6.5. So I'm talking of 1500 divided by 230. So this is equal to, let me just put it here. This is about 6.5 amps of current. And 6.5 amps of current.
jaldi aa jao. Jaldi kar le.
Okay. All right.
Dimple ma'am, can you mute your phone, please?
I'm really sorry.
Okay. Right. So we got an understanding of circuits in terms of what happens. Now all I have to do is apply the V is equal to IR formula, and I know my whether I have so much of current available. There's one thing which I missed out here, which is the power formula, which is power is equal to voltage into current. The product of voltage and current is power, and which actually is measured in watts, wattage, WATT. Okay, cool. So let's go to the next slide. This is the resistor color code. So all of these resistors that you see here, we cannot type the value of the resistance on this because it's very difficult to print. So what they do is they do color bands on these resistors, and the color bands is easy to identify using this formula. There are a lot of stories and easy ways to remember this. One of them goes like B.B. Roy of Great Britain had a very good wife. So this is how we learned in school. I don't know if you have a different formula, but this is B.B. Roy of Great Britain had a very good wife. So this is how it is. Lucky B.B. Roy.
Same way only, sir.
Same thing. Okay, but I've also heard a different thing. It's also another way of remembering the planets. My very intelligent mother had
shown us 9 planets.
for 9 planets, but we don't have the 9 planets anymore. So yeah, there are very easy ways of remembering this, and it's very easy. I mean, today you don't have to remember all of this because within just about 10 seconds, you ask Alexa what is red, red, brown. It will tell you, okay, it is so many kilo ohms of resistance. So the students are finding it very hard to understand why should we remember all this? Why should I always look at a resistor and calculate the color code when I can just type on Google and Google tell me what color code to use, right? So this is the challenge with the current transition that we are going through, and as a generation of educators and learners, we will have to go through this transition in terms of technology overtaking what we ought to learn in terms of books and the regular learning that we had, and what students are, they're very right in asking the question, why should I remember all of this? And at the same time, we'll also have to tell them the importance of doing it and learning it, and why it will really come handy. Because I remember one of these places, I mean, in fact, we will see it when we do a sample circuit, that you cannot always go back and check Google in terms of what this particular code. So when I say brown, black, red, it is 1 kilo ohm. Brown, black, orange is 10 kilo ohm, and brown, black, yellow is 100 kilo ohm. So this is something that we used to very commonly remember in college days when we used to build robots, because these are very common resistors we used to use. Okay, right. Another thing that I want to tell is the tolerance. When I say tolerance, nobody will be able to manufacture exactly 1.0000 kilo ohms of resistance. Every resistor will have a tolerance, like plus or minus 10%. It could be 1.1 kilo ohm, or it could be 0.9 kilo ohm. So it could be 900 ohms all the way to 1100 ohms. That's the reason why the plus or minus 10% is there. And there are very good resistors which give you 0.1%. These are called military grade resistors, and these have very specific applications in electronic circuits. They're a little expensive, but they have very specific applications in electronic circuits. Coming to electronic circuit symbols, most of you would know the symbols that I've mentioned here. This is a diode, this is a capacitor, this is an inductor, this is a resistor, looks like a speed hump, right? That's the reason why that's the function of a resistor. This is a DC voltage source, like a battery, and this is an AC voltage source, like your home appliance, home power supply. Now, if you want to use the same thing and be able to show LED in the diode, if you want to say LED, you just have to put a arrow mark like this. This is a light emitting diode, which is a LED. Capacitor, if you have a shape like this, you can call this the negative side of the capacitor. Inductor same, resistor same, DC voltage source, yes. This is a meter, which is measuring current. Two ends, this is called the ammeter, and this is actually called a voltmeter with V. These are very common circuit symbols that we will be using. Very rarely we'll go for anything else. So for example, how do you depict a motor? So motor is depicted something like this. These are like the two brushes of a motor, and they say this is the motor. This is a circuit symbol of a motor. There are various ways of doing it, but this is how we depict a DC motor. Anything else? That's, yeah, there's something called transistor. So this is a transistor. Yeah, this is a transistor. I think we will not go anything further than this, at least in the school robotics level. But definitely there are like 100 other components that could be represented here, which I'm not covered for a particular reason that we will not have to go through and make it very complicated. So these are the basic electric symbols that you need to keep in mind. And just clear this for all of you, and then we will get into the basic electronics kit. So what I show you here is a simple electronics kit. A lot of it is available on Amazon, or it'd be available on in your local electronic shops. The first one is called a multimeter, which is having a meter and a voltmeter in the same device. Just by connecting the wires in different way, you can use it as a multimeter. I mean, a meter or a voltmeter. That's why it's called a multimeter, because it can measure current, it can measure voltage, it can measure resistance. It can also check for continuity, if there is a continuous wire, conductivity. And it can also check for diodes and LEDs. There's also a small blue feature here in one corner. This is for testing transistors. Okay, this is called a breadboard. What you see second is a breadboard. When I say breadboard, you can consider this to be a bread. Why bread is because if you put a pin on the bread, it will remain the way where it is, right? And there are a lot of pores in a bread, and this is also considered in the same way. And the way this is done is what is important. I mean, the way it is constructed. A breadboard internally has long strips of conducting plates in which the holes which are arranged here, they're arranged in a particular fashion. So if I have to show you how these holes are arranged, I would be able to show you this way. So for example, these holes are connected to each other like this. Okay, these holes are connected to each other like this. And if you connect here or here or here or here or here or here, all these components that you connect there will be touching each other. Okay, and on the other side is the same thing. These lines are connected to each other. These lines are connected to each other. These lines are connected to each other. Okay, there is no connection between this point and the next point. And also, if you see, these connections are made in such a way. This entire thing. Oh, sorry, that's not red. Same. Yeah. So this is connected to each other. This one. This is connected. This is connected. This is connected. Okay. And they've also mentioned explicitly that this entire thing is connected. It's nothing but a conductive plate which is below these pins. So it's easy for me to identify, I mean, want to make multiple connections, I'll make multiple connections. Same thing here. This entire thing is connected. Maybe you can use this as negative and use this as positive. And this is a breadboard. There are multiple breadboards. They come as small as this to large breadboards used in complex circuits, in simulating complex circuits. But there are a lot of challenges with breadboard, primarily because breadboards do not give you a foolproof way of testing some circuit. Like sometimes the connection might be loose, the wires would have come out, or something would have gone wrong. So it doesn't. You can only test for working of a circuit. You cannot test for non-working of a circuit. So if you have a circuit, you want to test the circuit, and if the circuit works on a breadboard.
Okay, children, all of you join the new classroom. Okay, I will call the attendance. I will in the old one. Okay, I will send the class code once more here.
Okay.
Good morning, ma'am.
All right. Good morning. I do understand there are classes going on and all of that. Right. Great. Coming back. So this is what breadboard does in terms of what function it is. And these are all electronic components. What you see here is like LEDs, diode, resistor, LDR, and there's a battery, there's nuts and bolts, sensors, Bluetooth module, sensor, a controller, buzzer, switch, motors, and all. You get basic electronic kits and multiple electronic kits available. This one is actually from our own, this is one of our products, which is called the Make Many Robots Kit. And this is available on the website. And this is the basic electronics kit. Going further to simulate these circuits, to understand a little bit more about electronics, we will get into Autodesk Tinkercad. I had asked a lot of you to create account yesterday in this one. This is a completely online tool. And previously, when Vibha was conducting the session as well, he demonstrated on the Tinkercad. It is a beautiful tool, especially when it comes to doing small experiments or small hands-on sessions. Because you do not have a kit with you, we can actually try on this, and it's pretty, in a way, I would say it's good in terms of what all goes on. So there's one thing where I say I connect a LED to a battery and the LED bursts. This is something that may not happen in Tinkercad, but that experience of the LED bursting and then me realizing, oh, I have to connect a LED to a battery along with a resistor only. That's a life experience that I would gain, which is missed out on a online platform. But at the same time, it enables a lot of people to be able to test even without a component. So this is the advantage of Tinkercad. So what I'm going to do right now is share my screen for the website where we are having Tinkercad. Great. Let me share and share. Okay, I hope my thing is clear. Okay, let me just log out from Vibha and log in again through Brajesh's account. Yeah, so this is what comes when you go to tinkercad.com and then you sign in. I use my Autodesk email ID, Brajesh. Sign in. Okay, cool. So this is my profile where I create design. You saw 3D designs in the morning. What I'm going to do right now is circuits, and I say create a new circuit. The next half an hour is going to be more into understanding different circuits and trying to figure out what to do, how to do, and all that. Let's start with a simple LED, right? So I have a LED. I'm just going. Oh yeah, by the way, you don't have to do anything much. You just can just start off right away. There is nothing like, okay, I need to wait for a lot of time before. I mean, I have to do some presets before I begin. Nothing like that. You can just drag and drop. I just dragged and dropped LED here. It'll ask me, do you want to name it? I say yes. I call it LED. And what color do you want it? I give it red. I'm going to ask a very interesting question. If you could answer, it would be great. As in terms of, I'll just ask in a while. So this LED is having a cathode and a anode. Now, what is cathode? What is anode? Anode is supposed to be the positive. Cathode is supposed to be the negative. Yes, no?
Yes, sir.
Yeah, right. So I have a LED. Yes, and I have a battery. I'm going to just place the battery. I just will rotate the battery so that it's easy for me to put it here. Can I just do this? Yeah, I just made a connection. And then I start my simulation. Nothing happens, primarily because I've connected the positive to the positive of the system. 1 second. And interchanged it. So I'm going to make the connections this way. I just have to click on this and click to this and click on this and click to this. Okay. So once this is done, this is exactly what happens when you give a battery to a student and give them LEDs and say, wait till I tell you till I tell you to connect. Do not connect the LED to the battery. And by the time you tell this and start distributing the components to the students, you will have heard a few blasting of LEDs in one corner, because one student would have already connected LED like this to the battery and the LED would have burst. And this is what is going to happen here. Okay, it says the LED bursts. But interestingly, look at what it says here. It says the current through the LED is 915 milliamps, whereas the absolute maximum is supposed to be 20 milliamps only. Okay, which means almost equal to 1 amp of current is gone through that LED, where the LED just consumes 20 milliamps. Almost 50 times its capacity is what you have given through this, and because of which there is the circuit burnt. Now, how do I avoid it? I could probably use
resistor along with it.
Yes, I have to slow down the amount of electrons that flow per second, or the rate of flow of electrons is what I have to reduce. Not the number of electrons, but the rate of flow of electrons. What determines the number of electrons? This one, whether I give 9 volts or 20 volts or 100 volts. But what determines the rate of flow of electrons is the resistor. So I'll delete this and I'll put in a resistor. Okay, it says it's brown, black, red. What is brown, black, red? I told you that time it's 1 kilo ohm. And if I want 10 kilo ohm, it's gonna become orange. See this? It's become orange. Okay. And if I want 100 kilo ohm, it's gonna become yellow, and 1 mega ohm is gonna become green, and then blue, and violet, and goes on. Okay, so I am just putting a 1 kilo ohm resistor. It's a very commonly used resistor, 1 kilo ohm. So somebody might tell you, I need 980 ohms. So what will you do? You can give them a 1 kilo ohm and say you can use it. It will still work. The circuit will still work. You don't have to be very precise with resistors. That's the reason why we have another combination circuits that come, where I'm okay to have the resistor go a little here and there, but it's not like I need my LED to glow at the same exact brightness that I want. It's not that. You want just the LED to turn on, so you don't have to worry about the resistance. So let me put 1 kilo ohm resistance. I'll say resistor 1. Okay, so this is resistor 1 and done. So what I have to do is one end of the resistor I connect it to the anode, the other end of the resistor I connect it to, okay, I connect it this way, and then I start my simulation and I have my LED glowing. This is something that all of you can do on your computer, even maybe your mobile phone. All you need is a browser account and start doing this, and do as much experiments as you want, because if I had to do this practically, I would have lost 50 rupees by now to get this LED to glow properly. 10 LEDs burnt and then battery drained out and all of that. Okay, so let me stop simulation here. So this is with a LED. Now let me just change this resistance to say 1 ohm. Okay, and let's see what will happen. LED burst. Oh, which means because it's 1 ohm, I have a lot of current flowing through the circuit. Yeah, what is the current flowing through the circuit? It's about 800 milliamps. Oh, then I say, let me try with 10 ohms. Again, the LED bursts. Okay, I'll try with say 100 ohms. It's too high. It's about 65 milliamps, but the LED might just burn out anytime. Okay, so a good maybe 500 milliamps. 500 ohms is gonna do the job. Yes, 500 ohms is doing a job. It's doing a good job in glowing the LED. The LED will be brightest at a particular value. After that, the LED's life will reduce or LED will burn off and all that. So this, as and when I am changing the value of resistance, I see that the LED brightness increases and reduces. So instead of using a resistor here, I can use what is called as a potentiometer, which is a
variable resistor.
Variable resistor, resistance that I can keep changing with time. I mean, with my actions. So here there is something called as a potentiometer, but potentiometer has 3 terminals. Okay, how does this potentiometer actually is in when it comes to the construction is just this. It is a resistor, and then there is one connector like this. So you see 3 terminals. This is nothing but this. This is nothing but this, and this is nothing but this. Okay. So this 3 terminals of a potentiometer. So effectively what happens is, if I take this point and this point is exactly the center, which means if this entire system is 1 kilo ohm, then this is going to be half a kilo ohm, which is about 500 ohms. And this is going to be 500 ohms. Suppose I say this is not what it is, and I bring in this end to this end, extreme end. What happens? It's going to be 0 ohms, because the current will just flow from here to here. Why will it go through the resistor? And if I'm using the extreme 2 ends, if I'm using the extreme 2 ends of the resistor instead of using the center, I will exactly get 1 kilo ohm. No variable. Even if you rotate the pot, do anything, nothing's going to happen. It's going to be the same. Let's see the same circuit here and try replacing the circuit. Clear all drawings. Yeah, so what I'm going to do is I'm going to replace this and say this is going to be 1 ohm, okay? Because I know 1 ohm is going to be very less and I don't have to worry about it. But at the same time, I will create a potentiometer here and connect wires from this point to this point and this point to this point, okay? Now this is what it's supposed to happen. What happened? The LED glow. Okay, it doesn't act as a fixed resistor. Let me just change this. It will act only as a potentiometer. So I'll have to connect this. This. Okay. So let's see if it works. LED is still glowing, and I'm able to. Okay, the LED burnt. There's a particular value at which LED will not burn. See that? I said this is actually a 250 kilo ohm resistor. So let me just bring it down to say 10 kilo ohm. The total resistance is about 10 kilo ohms. Hey, okay, sorry. I think that actually the previous circuit worked because I had done this to be 250 and that's the reason it was not working. Okay, now what I'm doing is, irrespective of me moving the dial, the resistance is not changing because I've connected the extreme ends of the potentiometer. I've connected the extreme ends of the potentiometer. That's why the rest thing is not moving. The LED is glowing. The LED is still glowing. Now what I do is, instead of that, I will just connect one end of the system here, and then try rotate, start simulating. And you see, when I'm here, 1, 2, 3, 4, 5, 6, 7. So it's about 10 divided by 7, about 2 kilo ohms every dial. So it's about 2 kilo ohms. Now it's about 1 kilo ohm, and then it's increasing its brightness, and you see it suddenly burnt. Now, how about me changing this value from this 1 kilo ohm to 10 kilo ohms to 1 kilo ohm. So the LED is brighter, and then it starts becoming brighter, and then burns, because this entire thing now is 1 kilo ohm. Okay, that's the reason when you're using a potentiometer, we always ensure that this is at least of a particular value which will not spoil the LED. So we say this should be at least about 100 ohms. So no matter what you do, you'll only see that the resistance, the LED is not burning, but the brightness is increasing and reducing. See this? You'll see that the brightness is reducing and increasing, but will not burn, primarily because there is one resistor which is of a particular value here, which is ensuring that the current does not exceed a particular value. What is the current? When this becomes 0, the current is almost 64 milliamps, and I'm ensuring that my LED is still glowing, it is not burning. Okay, great. Also keep in mind that this value that you calculate here in the simulation will not be the same on the circuit, because every LED manufacturer will have a different way of putting things. It might be dark red or it might be a light red color, and depending on the wavelength, the resistance or the effective current required by the LED will also change. Which means tomorrow, if you're changing this into a white LED, you will see that you can put a little lesser resistance here and be able to still glow the LED, which means white light is okay to consume a little more current when compared to red. Or if you're using something like blue, the blue can take a little more current when compared to red. Okay, so I'm just stopping the simulation. I'm just putting this on one side. Let us do a small experiment with respect to resistors. Okay, cool. So I'll bring another resistor. Okay, cool. I have two resistors that I've placed. I'll bring a 3 volts battery. Okay, and then I will just bring maybe, what do you want? Yeah, there are a lot of components. You can just see all the components that you can actually start using. We will do about 3 or 4 experiments, and then you can do at your home. And in case you have doubts, you can always ask. Okay, let me just get a voltmeter. I want a meter to actually measure the voltage. Yeah, I have a multimeter. I'll bring a multimeter. I want multiple multimeters, not just one, to just measure what's happening. Okay. Then I say, now let me just connect the positive of the battery to one end of the resistor, the other end of the resistor to here, and then this end to this end. Okay. Yeah. Now what will happen when I do this, when I start simulation, is electrons will start moving from the negative end of the battery all the way to this and start coming here. The current will start moving from the positive to this side, right? Now I want to measure the current flowing through the circuit. So what I'll do, I'll delete this and then connect this to this. No. Okay, it's just that it will show me a negative voltage. Okay. Hold up. This I'll connect to the positive, and then this I'll connect to the negative. Okay, great. Now what I want this to be, I want this to be a ammeter, amperage, and not, sorry. Yeah, so I want this to measure current and instead of voltage. So what I do next is to run my simulation. I will say ammeter 1. Okay, and then start simulation. It's about 1.49 milliamps of current flowing through the circuit. Okay, if my wire that I'm using, okay, remember this, if I'm using a wire which can take 1.49 milliamps of current, great, my wires will not burn. But if I'm using, suppose this is 1 kilo ohm, I make this 100 ohms. Oh, sorry, not 100 ohms, 100 kilo ohms. This 100 ohms. Okay, the current is this, and this also I change to 100 ohms. See the current flowing through the circuit. Suppose I change this to 1, and this is also 1. 250 milliamps of current. You know what will happen now? This battery which is here will burn out, which means it will just drain out completely. This is something that you cannot learn here in the simulation, but if you actually try doing it, it will drain out, because if this battery, if you draw this much current from this battery, then the battery will just drain out within seconds. So let me just replace this battery and with a 9 volts battery. Yeah, so you see the amount of current. Do you make out the difference between that battery and this battery? That was 250 milliamps, and this is 2.57 amps.
Sir, can we add potential meter also, sir, if it is possible?
Yes, ma'am, we can add potentiometer. But what I'm trying to ask you is, why did the current change? Because I changed my battery. And I just increased the battery voltage by 3 times. My current almost increased by 100 times. Or maybe 20.
It is because the resistance, the amount of resistance, since it is constant, so we know by Ohm's law, V is directly proportional to I. Since we are increasing the potential difference, the current is also going to increase?
Yes, correct. So, exactly. And because I'm drawing 2.57 amps from this circuit, the wires that I'm using, if you use the same wires that I showed you a while ago, the breadboard wires, the wires will burn because the wires are not capable of handling 2 amps of current. They're only 1 amp wires. You can handle maximum 1 amp wires. So you should always be careful with the value of resistors that you put and all that. And that's the reason why we encourage simulation before you actually try out something in practical. Okay.
Excuse me, sir.
Yes, ma'am.
Sir, before you used a coin cell 3V battery, na sir. You told that it is burning. How we have to identify? Because that LED and all the burning symbol it is shown.
Correct.
But here, how to identify that, sir?
Okay, you will not be able to identify the burning. See, the battery will not burn. When I say burnout, I mean to say that, see, you have a battery and suddenly you give it to a student, and then after 2 minutes, they'll come and tell you, ma'am, this battery is not working. You give them another circuit, another battery, and then after another 5 minutes, they'll come and say, ma'am, this battery is not working. Why will this happen? This is happening because, let me show you. I take a battery. This is the battery. What they do is, they connect a wire from one end. Let me put it on a multimeter. Okay, and let us make this current. Measure the current. Let's measure the current that's through this, and let's start simulation. You know what will happen? I am trying to draw 6 amps of current through this battery. It's a very small battery. Maximum it can give is about 200 milliamps or 300 milliamps of current. If you draw 6 amps on this battery, don't you think the battery will fully drain out within a few seconds?
Yes.
Yeah. So they come back to you telling, ma'am, it's not. So you give 10 batteries and then you realize, oh, I think in the circuit, the student has connected the LED somewhere. For example, you see the student would have connected the LED here. And he would have also connected another wire from positive to negative.
Okay.
So he will do simulation. The LED will not glow. The battery is drained out primarily because the connection, there is a mistake. So if you see something is wrong, you should always go back and check if the connections are made proper.
Thank
That's
you,
the reason it's important for you to check on the breadboard. Okay, has the wires been connected properly? Have they connected the positive and negative so that the entire circuit is not working? The battery is getting drained out. Suppose you have a power supply. Instead of this, you have a very good power supply like an adapter, or you have the regular 230 volts AC that you're using. You know what will happen if this happens? It's nothing but a short circuit. The current is flowing from this point to this point and not through the LED. So it will actually cause a short circuit. And if the current is more, then the wire might burn. Small wire burns like this. But if it's thicker wire with a lot of PVC coating on it, then it will start catching fire. And that will lead to short circuits at homes and industries. All that happens is somebody is connected the positive and negative wire with a conductor, or where there's very less resistance in the circuit. Okay, cool.
Thank you, sir.
I'm just putting this a little away, and we'll come back to the small circuit that we did. I was trying to teach you a little bit of understanding voltage division, how voltage division happens.
Sir, excuse me. How
Yes,
to
ma'am.
fix the LED on breadboard? How do we decide this is positive, this is negative?
For a LED?
Yes.
Okay, there are 3 ways to identify a LED. I don't have it in my picture. Let me see if I can actually share it with you. Okay, I'll explain you here itself. In a LED, the longer lead is the positive, the shorter lead is the negative. Okay.
Yes, sir.
The longer lead in the LED is positive and the shorter lead is the negative. Second thing, the LED will always, the negative part of the LED will always have a flat zone when compared to the other part, which means when you look at the top view for a LED, do the top view of the LED, it will look like this. There is a flat zone on the negative side of the LED. So this is negative and this is the positive of the LED. This I'm talking about the top view of the LED. When you look at the LED from the top, this is how it look like. There's one notch, this is called a flat notch on the negative side of the LED. Why is it important? Sometimes what happens, the students will cut the wires of the LED and make it both equal and tell you now identify which is positive and negative. This has happened to us over years. So how do you identify then? You identify by the notch. There's a physical notch on the LED. So that's the reason why you see here, it's a flat when compared to round. The flat side is a negative, the round side is the positive. Another way of looking at LED is a notch that's inside the LED. Suppose you have something like LED which is translucent, where you can see what is inside the LED. There you can determine it by this way. There is a part like this, and then there is a part which is like this. So the one which is wider is actually the negative, and one which is smaller is the positive. Okay, this is how it is inside a LED.
Sir, I have seen LED bulbs transparent, but it gives different color. How does it give?
When you turn it on, it gives different color, or are you talking about RGB LED?
No, I don't have any idea about.
Okay, you just connect the power supply, it will keep glowing blue, green, yellow, blue, green, yellow. That's what you're telling?
Yeah.
Yeah, that's because of the material used here. The semiconductor material that is used, they change the doping in such a way that the electrons jump from one orbit to another, and they emit different lights as and when they come back. So multicolor LED is what they're called. It is primarily because of the content of the doping that is done on this semiconductor here.
Thank you, sir.
Okay. So this is how you identify LED. One is by the length of the lead. The second thing is by the notch on the negative side. The third thing is the internal of the LED. The wider part of the LED is actually the negative or cathode.
Excuse me, sir. When I opening my Tinkercad, I can just able to draw some 3D diagrams, but I want to know from where you have got this circuits and all, sir. Where should I go? Sorry, I missed that part.
No problem. You have in 3D designs, and then the next
Yes,
one
sir.
is circuits, then is code block.
Okay.
Yeah, so you select circuits, and then what happened to my circuit? Oh, okay. I think my circuit is gone. Oh, it's here. Where is this? Where is this? Yeah, this one.
Got it, sir. Thank you very much.
No problem, ma'am. Okay, so the last experiment that we'll be doing, you can do a lot of these things. There's a push button, you can put a switch instead of here. Let's just put a small switch, just remove this and put a switch here. And then you will see when I'm simulating, I'll see when I press the switch, the LED will turn on. Okay, I can do that. There is a switch available. There are breadboards available. You can use a breadboard, try it out. Motors are available. So let me just bring a motor and connect to, instead of the LED, instead of the LED, I'll just connect this to a motor. This goes to this, and this goes to this, and then when I start simulation, your motor is rotating at a very low RPM, which is 0. Why is this so? Because I'm not turned on the button. Let me turn on the button. It says it's rotating at 6,839 RPM. That's because of this. Let me see if I can actually decrease the speed by increasing the resistance. I increase the resistance a little more. I'm able to increase the RPM. Okay, as in when I decrease the resistance, RPM increases. Okay, and the reason why you see it as minus 2651 is primarily because of the anti-clockwise rotation. If it's clockwise, it's going to be plus. Anti-clockwise is going to be minus. That's because I connected the positive to negative, negative to positive to the motor. Always remember, motors don't have polarity. There is no polarity in a motor. What motor rotates like this in one direction, when you look at from the other direction, it rotates in the anti-clockwise way. So motors don't have polarity. It is just a coil of wire, like how resistors are. Motors don't have any polarity. But for our understanding, what we make on a motor is the red wire if you connect to positive, the black wire if you connect to negative. The motor will rotate clockwise. That is the understanding from our perspective. But motors as such don't have negative and positive.
Sir, where can you see that it is rotating? Like, I cannot make out that the motor is rotating or not after simulation is done.
Yeah, so yeah. So you'll see that the motor is rotating, where it mentions the RPM here. You see this 0 RPM mentioned. So you'll see that RPM changes. It says 1,399. You'll be able to see it when you do it on your screen, on your browser. Okay, cool. So this is with respect to circuit, Tinkercad. A lot of experiments can be done. See, you have a hobby guide motor that you have. You can measure the current of this motor by connecting it to 9 volts, what's happening and all that. So all of this is great. I just wanted to show one small experiment with this battery, and we just went somewhere else. Let me just show you that. So I was just talking of using resistors and trying to measure the current. So I will just delete this. Now I want to measure the voltage across the resistor. Okay, this, and then I have a wire connecting from this end to this end, this end to this end. I have one more multimeter which I'll connect from here and across this. So what I'm trying to do is I'm just measuring the voltage across the resistors. I've just connected the resistors in series. This needs to be voltage, voltmeter. Okay. Leave the other circuits in place. Just start simulation. You see, this is 9 volts, and you see about 2.57 volts across this and 2.57 volts across this. Primarily because the battery is already drained out, and you put just 1 ohm. Just put 1.1 kilo ohm and about 1 kilo ohm. Sorry, I have to do 1 kilo ohm here. Okay, and look at this. I have 1 kilo ohm here, and there is 1 ohm here. All the voltage will drop across the higher resistance. I've just put this resistance in series. All the voltage will drop across the higher resistance, and the remaining little voltage across the least value. So when you give a low resistance path, the voltage drop across it is very high, very low. So if I increase this to say 1 kilo ohm, I'll see that the value is 4.5 across this and 4.5 volts across this, equal. Red, black, brown, black, red, brown, black, red is nothing but 1 kilo ohm. And you'll see equally 4.5 volts across this, 4.5 volts across this. This is what is happening. This is how I use voltage divider circuits. To suppose I need to run a motor at about 4.5 volts, then I can use a voltage divider circuit like this and get it working. But at the same time, you should also remember, if I have to check the amperage of the current that is flowing between this point and this point, when I start simulation, you see it's about 4.5 milliamps. For motor, I'm not sure if 4.5 milliamps is sufficient. Motors require at least 300 milliamps. This motor requires 300 milliamps. So which means I cannot use a 1 kilo ohm. I have to probably use 100 ohms. And here also I'm supposed to be using 100 ohms. Yeah, maybe now your motor is rotating a bit because of some current that is flowing through it. Okay, so it's a very unique thing. All I'm doing is varying the voltage, current, and resistance to be able to do multiple applications using electricity. So this is what we do in Tinkercad, and this is exactly what we do on breadboard also. If I had to show this experiments on a breadboard and explain to you, it would have taken a lot of time, and you wouldn't get it until you do it yourself. But I want you to try this on the Tinkercad software in terms of what is possible. There's a huge possibility available, and you can get your basics in terms of electronics really well if you are able to crack this out. All see a simple thing, no? When I say why is it 4.47 and not 4.5? It should be 4.5 and 4.5, right? Because a meter is not a very I mean, it's not a current consuming device. The resistance of a meter is almost zero. But why is it 4.47 instead of 4.5? So these are questions that you're supposed to ask. Now, don't ask me because I don't know why it is so. But I would say this is causing some resistance to the circuit, and that's the reason why there's a little bit of.
Maybe due to the resistance of the connecting wires as well.
No, because I had the same amount of connecting wires before, and I used to get exactly about. This is supposed to be 4.5. No, but earlier. Hold on. Sorry. Yeah, that is primarily because of the resistance value and not the
resistance
connecting wires. Let me tell you what's happening. I told you when I use very low resistance, there'll be amount of heat that is generated. Yes or no? So this value is what? 100 ohms, and this is 100 ohms. You know, when I connect 100 ohms to a 9 volts battery, it's going to heat up like anything. And the voltage is actually going to actually heat up the circuit. So that's the reason why you will see that the voltage is dropped. See, all of this is a mathematical model. They have put it in a system and made a simulation. They have considered as much as possibilities as possible in terms of, okay, what current will LED burn? What will happen if I make a very low resistance? So for example, you remember earlier I had made this 1 ohm. And this had become 2.57 volts and 2.57 volts. I mean, where's the remaining 4 volts or 3.9 volts? It's not there. What's happening? The circuit is burning right now. The circuit is burning right now because I've just put 1 or 2 ohms in the circuit, and literally maybe my resistors are burnt and flying around here and there. Okay, so this is what happens, and this is how you need to learn electronics. And I'm happy that it is not like how we used to learn when we were in school and college. We literally have to do experiment for 3 hours to learn one small experiment. Here you can do multiple things and at zero cost.
Yes, sir, this is a very good platform, sir, and and also I think it's a free circuit design model, and where we are, sir, simulating different electronical components.
Yes, ma'am. Right. This is only for simulation. If you want to design your own circuit, you cannot use this software. There is another software from Autodesk called Autodesk Eagle, and you will have to use Autodesk Eagle to build your own circuit boards and all that. We do as sessions. Probably I'm not sure if we have some online tutorials on our YouTube channel, but there will definitely be some of the other tutorials that we have already done on PCB design and all that, so that you can refer to. So if you have not already checked out our channel, it is on YouTube. It is youtube.com/JustRoboticsIndia. That's the same place where you're getting the live stream and all of that currently. Hold on, I am supposed to give the attendance link.
It has already been issued.
It's posted on this one also.
On Zoom chat box, it is given.
Okay, I'll just have to post this on YouTube for those of them attending on the YouTube.
Mr. Brijesh, may I ask you one thing?
Yes, ma'am.
Sir, after actually going through these trainings from yesterday and today, I have come to know that I'm a computer teacher actually. So my concern is that way back 20, 30 years back, I have studied this physics and chemistry. Will I be able to teach my children this robotics, or do I need to take the help of physics and chemistry teachers also?
Not necessary, ma'am. So see, when we teach this concept, no, I am teaching it like how I am teaching to a student.
That is okay. But right now, what happens that we don't have much time to review the things, and from point of view of your exam, also on the last day, I'm just asking this thing. Would we be able to get that minimum pass percentage or not?
Yeah.
Level.
That you will be able to get. A very simple, easy question.
Okay. Thank you.
Sir, can we get the recording of this session? Because whatever you have explained, it's wonderful. But we are the slow learners. We have to repeat the thing again. So can we get the session recording?
Yeah, all the sessions that we have conducted are recorded, and it will be available on our channel. It will also be available on the ATAL link, and it will be posted to you separately as a mail with all the links put together, including the presentation.
Yes, sir. We have started.
Thank you very much, sir. Thank you.
You're welcome, ma'am. Thank you.
It's really a very good session. I loved it very much. And when we are going to join again, sir?
I think the next session is at 2 o'clock after lunch. The next session is going to be in programming, which Mr. Arun will be taking.
Thank you so much, sir. Really nice.
You're welcome, ma'am.
Wonderful session, sir. Really interesting.
Thank you.
You are a good teacher. Very good teacher.
Sir, you're a very good teacher. My daughter, she is also learning from you. She is fourth.
Oh, yeah, very good. That's wonderful.
Tough topics explained very easily, sir.
Yeah, sir, you are excellent educator. Means you have taught in such a wonderful way. That's amazing. Thank you very much.
Thank you, ma'am. I
It's a
just
very
hope,
wonderful
it was
software,
really
and
interactive,
we can
Sister.
make use of it very well, I believe. So thank you very much for
Sir, my son, 6-year-old,
giving us
also is getting so much involved in the pictures. You're amazing, sir. Amazing. Very good, sir.
Thank you.
Yeah, sir.
Thank you.
Brijesh, sir, you teach the basic concepts, sir. You clear the basic concepts.
Yeah,
Very well explained, sir.
Right. The intention here, why we doing this program is because, see, like we said yesterday, the robotics revolution is anyways happening. And if we try to do it all by ourselves, telling that I will go teach every single student, it's not going to happen. The only way to be able to capture and take our country or the society to a level where it is capable of working along with robots is to teach a lot of people at a very short duration of time so that they can teach the remaining people and go on. We want this knowledge to spread and reach out to most. We don't have another 20, 30 years to teach students all these concepts. Like all students currently in any class or school needs to know these concepts, because tomorrow they're going to somehow or the other interact with robots. And that's the reason why we are trying to democratize the whole STEM and robotics education. It should not be something that is possible only for the affordable or the affordable class of the society. So we conduct a lot of these programs with the government schools also, the government school teachers as well. So the idea is to be able to tell them simple basic things so that most of them think it's a very complex subject, very complex thing, and they don't even do it anytime. And that's the reason we want to break that myth and say, no, it is very simple, it is very easy, and this is what you can do. All right,
sir, these softwares are so good. I think 6th standard onward, if we give it to them, they should be.
Do you have some more questions? Hello, participants.
Yeah.
Sir, what is the simulator time which is being running out on the board?
It will keep running on the thing.
Till we do it.
Yeah. So it's basically, say for example, there are things like function generators and oscilloscopes for keeping time in picture. Yes, ma'am.
Yeah. Have you completed the session?
Yes, ma'am. Done with the session. I'm stopping the live stream now. I think I'd given the attendance link also on the session. But there are people who are messaging telling the attendance link is not opening.
No, there. I think I have mailed the session 4 also, the first session for the day, and the second session also. All the material will be available in the live stream YouTube. It is already available. You can just log in there and see the YouTube link. You will get all the material, audio, video, everything of whatever is done. Anyway, end of the day or end of the FTP will be sharing with you all the materials. Okay. So you have any more questions you can ask?
Ma'am, there are people on the YouTube live stream telling that the attendance link is not opening.
I have sent it here.
Yeah, we've posted on the YouTube link as well.
Okay.
So they're telling it's not opening.
Yeah, we'll just check that. Okay, and resend that link again. Okay.
Yeah. Maybe you have to enable that for a while.
Yeah.
Okay. Ma'am, I have received all the mails which you have sent, ma'am.
You have received all the mails which you have sent.
Yeah, ma'am. Yeah. All the sessions, YouTube link, everything.
Yeah, it's available in your this. If you log into that YouTube, you'll get all the information. Both whatever is done in the class, the same thing will be played there. Okay. So anyway, end of the FTP, we'll be sharing you all the information which is there to your email ID which you have shared with us. Okay. Thank you, Brijesh, for a very wonderful lecture and educating the participants with the basic knowledge on robotics.
Thank you, ma'am.
Yeah.
Yes, ma'am, I have received the mail, ma'am. Yesterday's YouTube link I have received and I could see that.
Yeah, I think if you log into that YouTube live stream which is going on now, that link will give you the yesterday's, today's, all the sessions which has been done already.
Even you have mailed us also.
Anyway,
so
we
I
will
can
share
see
with
that.
you all the details.
Yes, ma'am. Yes. Thank you very much for that.
Have a nice day. Okay, thank you, Brijesh.
Thank you, ma'am.
Thank you, ma'am.
Thank you, sir.